In this lecture video, we're going to see how to follow up an analysis of variance and perform specific comparisons. For each I going from 1 up to t, let y bar sub I dot be the mean of a random sample of size n sub I from a normal distribution with mean mu sub I and variance sigma squared. Then y bar sub I dot has a normal distribution with mean mu sub I and variance sigma squared over n sub I. We also assume that the samples are independent of each other. Now let a1, a2, and so forth up to a sub t be fixed constants, and consider the linear combination of the sample means given by using those constants as the coefficients in the linear combination, as you see here on the slide. Now it can be shown that the random variable given by this linear combination has a normal distribution with mean given by the sum I going from 1 up to t of a sub I sub mu, times mu sub I. So this is the same linear combination as in the linear combination of the sample means, but of the population means. So that is the mean of the distribution of the linear combination of the means. And the variance of this linear combination is sigma squared, the common population variance, times the sum I going from 1 to t of a sub I squared over n sub I. Now, if we standardize the linear combination by subtracting off the mean of its sampling distribution and dividing by its standard error, all right, which is the square root of the variance that we found on the previous slide, then that standardized version of the linear combination of the sample means has a standard normal distribution. Now, we don't know sigma squared, but we do have an estimate of it from the analysis of variance. In particular, the estimate of sigma squared, you'll remember, is the mean squared within, also called the mean square error. And so if we replace the unknown sigma squared by its estimate, sigma hat squared, which is the mean squared within, then the resulting random variable, the studentized version of the linear combination of the sample means, has a t distribution with n minus t degrees of freedom. And the reason it has n minus t degrees of freedom is because that is the number of degrees of freedom associated with the mean squared within, and you'll recall that from the ANOVA table. Now, in addition, if we square that random variable so that we get this quantity here, then the squared version of this random variable has an f distribution with one numerator degree of freedom and n minus t denominator degrees of freedom. Now, if the constants a1, a2, and so forth up to a sub t are such that their sum is 0, then the linear combination that results from using those as the coefficients is called a contrast. And contrasts are used to test custom hypotheses and construct confidence intervals for specific linear combinations of the population means that are of interest in a particular situation. And so we can use this information to come up with a procedure for testing hypotheses about linear combinations of population means, and also to come up with procedures for constructing confidence intervals for those same kinds of linear combinations of population means. And so the null hypothesis to be tested would be that a particular linear combination of the population means is equal to some specified value, which we would say, I'm going to denote here delta 0, against the alternative hypothesis that that linear combination of the population means is not equal to delta 0. Now, in many cases, delta 0 will be 0, but it doesn't have to be. It can be any value that makes sense in the context of a particular problem. Okay, then we form the test statistic, which is a t statistic, so we'll call it t-calc. And the test statistic is given by the same linear combination, but of the sample means. Okay, so you see we have the same a sub i's that we had up here. And so it's the linear combination of the sample means minus the hypothesized value, delta 0, divided by this estimated value of the standard error of the linear combination of the sample means. The rejection criteria is to reject the null hypothesis if the absolute value of t-calc is greater than the upper alpha over 2 percentage point of the t-distribution with n minus t degrees of freedom. And so this is a two-tailed test, a two-sided test, and so that is why we've got this. This is just another way, this rejection criteria here is just another way of writing a two-tailed rejection region. A 1 minus alpha times 100% two-sided confidence interval for the linear combination of the population means is given by a point estimate of that linear combination, which is the same linear combination but of the sample means, minus plus the interval coefficient comes from the t-distribution with n minus t degrees of freedom, and then we multiply that against the estimated standard error of the linear combination of the sample means. Now, an alternative test statistic is to use the squared version of t-calc, and we could also just call this f-calc because the reference distribution for this particular test using this alternative test statistic is the f distribution. All right, but I'll just call it t-calc squared here. And so if we're using the squared version, then we would reject the null hypothesis if t-calc squared is greater than the upper alpha percentage point of the f distribution with 1 numerator degree of freedom and n minus t denominator degrees of freedom. Now here's some examples of some specific hypotheses and the corresponding contrasts that we would use to test those hypotheses. Let's assume that we have 4 population means that are being compared in the analysis of variance, and then we're following up with some specific comparisons of interest. So the population means would be mu1, mu2, mu3, and mu4. And suppose that we specifically want to compare mu1 and mu2. All right, and we're going to do this using all of the data because we're going to obtain from all that data the estimate of sigma squared. And you'll remember that we get that from the ANOVA table, and that estimate is given by the mean squared within. And so that is when I say we're using all the data to make this comparison. Obviously, only some of the observations are from population 1 and some are from population 2, but all of the data are used in coming up with that estimate of sigma squared. And so in order to compare mu1 and mu2, we would do it typically through the difference, mu1 minus mu2. It's perhaps more natural to write it as mu1 equal to mu2 in the null hypothesis. The alternative hypothesis being the opposite of that, so mu1 not equal to mu2, but then we would translate that into a difference, and so the null hypothesis would then be mu1 minus mu2 equal to 0, and the alternative would be that mu1 minus mu2 is not equal to 0. Now we're going to use this linear combination of the 4 means to come up with the contrast coefficients, the coefficients that we'll use, and we can see here that for this linear combination, a1 would be which is the coefficient on mu1 would be 1, a2 the coefficient on mu2 would be -1, and then since mu3 and mu4 do not show up here, the coefficients on those two means would be a3 equal to 0 and a4 equal to 0. Now, another possible comparison of interest would be to compare the mean of population 3, mu3, with the average of the population, the means of populations 1 and 2. So, which would be mu1 plus mu2 over 2. And so the null hypothesis, one way to express the null hypothesis for that comparison would be that the mean of population means 1 and 2, so mu1 plus mu2 over 2 is equal to mu3, against the alternative that mu1 plus mu2 over 2 is not equal to mu3. Now we can re-express that as a difference, and so doing so, the null hypothesis would be mu1 plus mu2 all over 2 minus mu3 equal to 0, and the alternative would be mu1 plus mu2 all over 2 minus mu3 not equal to 0. And so we see then that the appropriate or the corresponding coefficients for that comparison would be a1 equal to 1/2, a2 equal to 1/2, and then a3 equal to -1. Now, these hypotheses can be written differently without the fractions by multiplying through both sides of each of these hypotheses by what's in the denominator on the left-hand side, so 2. And so when we do that, the null hypothesis would become mu1 plus mu2 is equal to 2 times mu3. The alternative would be that mu1 plus mu2 is not equal to 2 times mu3. And then re-expressing as a difference, the null hypothesis would be mu1 plus mu2 minus 2 times mu3 is equal to 0, against the alternative that mu1 plus mu2 minus 2 times mu3 is not equal to 0. And then expressed this way, the coefficients would be a1 equal to 1, a2 equal to 1, a3 equal to -2, and a4 equal to 0. And so either set of coefficients would result in the same test being performed, and so therefore the same results. Suppose that we want to compare mu1, mu2, and mu3. And so the null hypothesis would be that mu1 equal to mu2 equal to mu3 against the alternative that the three means are not all equal. In other words, at least one of the means is different than the others. These hypotheses can be rewritten using the following two sets of hypotheses. So the first set being mu1 equal to mu2 versus the alternative that mu1 is not equal to mu2. Then re-expressed as a difference, it would be mu1 minus mu2 equal to 0 against the alternative that mu1 minus mu2 is not equal to 0. And so the contrast for that particular set, or that particular hypothesis, would be a1 equal to 1, a2 equal to -1, and both a3 and a4 equal to 0. And then the second, a way of writing the second set of hypotheses that would round out this particular comparison could be written this way. And so mu1 plus mu2 equal to 2 times mu3 against the alternative that mu1 plus mu2 is not equal to 2 times mu3. And then again expressing as a difference, the null hypothesis would be that mu1 plus mu2 minus 2 times mu3 is equal to 0 against the alternative that mu1 plus mu2 minus 2 times mu3 is not equal to 0. And so for this particular set of hypotheses, the coefficients would be a1 equal to 1, a2 equal to 1, a3 equal to -2, and a4 equal to 0. So the bottom line here is that in order to compare these three means, we need two sets of hypotheses that are being tested. And these two sets of hypotheses would accomplish that goal. This is because the null hypothesis H sub 0 that says that mu1 equal to mu2 equal to mu3, that is true if and only if the two sub-hypotheses H sub 0, 1, which says that mu1 is equal to mu2, and null hypothesis H sub 2, which says that mu1 plus mu2 is equal to 2 times mu3, H sub 0 is true if and only if H sub 0, 1 and H sub 0, 2 are true. Now these particular examples, these particular custom hypotheses or specific comparisons can be performed in SAS by using the contrast statement within proc GLM. So the contrast statement is a statement within proc GLM, and in the SAS code on this page, we're assuming here that the response variable is named response and that the classification variable is named pop. All right, and so we have the invocation of proc_glm. We identify the classification variable, which is pop. We have the model statement. We're telling proc_glm that response is the response variable and pop is the variable that identifies the different populations. And then to compare means 1 and 2, so mu1 and mu2, so to test the null hypothesis that mu1 is equal to mu2, all right, we would issue the contrast statement. And the contrast statement has associated with it, well, first off, the contrast statement itself. And then we have some kind of a label inside either single or double quotes, it doesn't matter, which identifies the contrast so that we can, or labels the contrast so that we can identify it on the SAS output. Then we include the classification variable that's on the right-hand side of the model statement, and we include after that the coefficients that define the contrast of interest. And so if we scroll back, all right, a few slides, then this is the comparison that we are implementing in that first contrast statement, and we see here that the coefficients are A1 equal to 1, A2 equal to -1, and then both A3 and A4 are equal to 0. And so we see here that those are the coefficients that we have. And so we know that this contrast statement is testing the custom hypothesis that mu1 is equal to mu2, and it's doing it in the context of this general linear model analysis of variance. And so it's using all the data in the analysis, only those observations that are either from sample 1 or sample 2 are used to estimate the difference in the population means, but all of the data are used in coming up with that estimate of sigma squared. Okay, then in order to, let me see here, in order to perform this specific comparison, so comparing the mean of population 3 with the average of the means of populations 1 and 2, all right, we see here that we could either use coefficients A1 equal to 1/2, A2 equal to 1/2, A3 equal to -1, and A4 equal to 0, or we could use the coefficients A1 equal to 1, A2 equal to 1, A3 equal to -2, and A4 equal to 0. Okay, and so again we have the contrast statement, and we have inside parentheses some kind of a label, some text that labels the contrast so that we can locate it on the SAS output. And then we have the classification variable that is on the right-hand side of the model statement. And then we include the coefficients that define that particular custom hypothesis. All right, and so we're using here the whole number coefficients. And so this would be testing that particular, let me see here. Yeah, it would be testing this particular hypothesis. Okay, and then finally we have, we're going to test this comparison. So the comparison of mu1, mu2, and mu3, so that the null hypothesis would be that mu1, mu2, and mu3 are all equal to 0 against the alternative that at least one of the means is different than the others. And so remember, this is going to take two sets of coefficients, two contrasts, all right? And for that reason, this is what's called a 2 degree of freedom test, all right? And so we have the contrast statement, and then text inside quotes to label the contrast so that we can identify it in the output. And then we have the coefficients for the two contrasts that we've identified that will allow us to make this comparison. And so I'm using this set of coefficients. And then notice, and then I've got the other set of coefficients. Notice before each set of coefficients I have to have the variable on the right-hand side of the model statement, the pop state, or the classification variable pop, and that these two sets of contrast coefficients are separated by a comma. Now I've put this one on a different line just for readability purposes, you don't have to do that. We could list this part of the statement right after the comma, but we do have to have the comma. All right, it won't run correctly if we don't have that. And so this would show up in the output, and there would be 2 degrees of freedom, 2 denominator degrees of freedom associated with this test. For the other 2 tests, these would be 1 numerator degree of freedom tests. Okay, so let's look at an example. Let's apply this to the rice example, the rice variety example that we've been looking at. And so in the rice variety example considered previously, we concluded that the 4 rice varieties differed in terms of their mean yield. Right? So that was the conclusion that we drew. We looked at box plots of the data, and we speculated which of the means were different, but we didn't necessarily make or perform any formal hypothesis tests about those where the differences were. And so what we're going to do in this example is follow up that significant overall analysis of variance, and we're going to identify specifically where the differences are. And because we have 4 population means that we're comparing, there are 4, choose 2, or 6 pairwise comparisons that we're going to be making. Now, you're not always going to want to do pairwise comparisons. In particular, if there is structure, some kind of a structure to the treatment structure, then that treatment structure may determine the kinds of custom hypotheses or specific comparisons that you want to make. But in this case, we have what is called a one-way treatment structure, and there's no, and neither, neither of these populations are considered the control, so to speak. And so we're really interested in all pairwise comparisons. And so there are 6 of those. The comparison of means 1 and 2, the comparison of population means 1 and 3, and then 1 and 4, 2 and 3, 2 and 4, and 3 and 4. All right, so those are the pairwise comparisons that we will be making. And so again, here is a graph showing the side-by-side box plots, and this gives us some information on what we might expect. But again, in order to draw formal conclusions, we need to perform these specific comparisons using the methodology that we've looked at. And so the first comparison we're going to make is a comparison of means 1 and 2. So mu1 equal to mu2 is the null hypothesis. The alternative is that mu1 is not equal to mu2, expressed in terms of a difference. All right, the null hypothesis is that mu1 minus mu2 is equal to 0. The alternative would be that mu1 minus mu2 is not equal to 0. The coefficients are a1 equal to 1, a2 equal to negative 1, a3 equal to 0, a4 equal to 0. This is the particular contrast of the population means that we are testing a hypothesis about, and the hypothesized value of that contrast is 0. Okay, so the test statistic will be the same linear combination, but of the sample means. Then we subtract from that the hypothesized value, the delta 0, which is the hypothesized value of the linear combination of the population means. And then we divide that by the estimated standard error of this linear combination of the sample means. All right, and so that is sigma hat squared, or MSW, times the sum I going from 1 to 4 of a sub I squared over n sub I. Now the numerator of the test statistic simplifies to y bar 1 dot minus y bar 2 dot. All right, and then we could calculate, plug in the MSW later. Once we do the calculation, we would plug in MSW and evaluate this linear combination here. All right, so but this is the form of tcalc for this particular comparison. The rejection criteria is to reject the null hypothesis if our test statistic, if the absolute value of our test statistic tcalc is greater than the upper 2.5 percentage point of the t-distribution with 12 degrees of freedom, which, if you look that up, it's 2.1788. Okay, so calculating the point estimate of mu1 minus mu2, that gives us a value of 56.25. The estimated standard error of that point estimate, doing the calculations that you see here, right? And so we plugged in, notice that we plugged in the value of sigma hat squared, which is the mean square within, and then we're calculating this linear combination of the square of the A values over the sample sizes. And so when we do this calculation, we get an estimated standard error of y bar 1 dot minus y bar 2 dot of 45.5868. All right, and so then calculating the value of the test statistic, we get 1.2339. Now, since that value is not greater than 2.1788, we fail to reject the null hypothesis. And so at the 0.05 level of significance, there is insufficient evidence to conclude that mu1 and mu2 differ, which is not too surprising because when we looked at these side-by-side box plots, the vertical location of these boxes really did not look that much different. I mean, and so that also tells us what to expect when we compare mu1 and mu3, mu2 and mu3, and so forth. Now, before we go on to the next comparison, we want to construct a 95% confidence interval for mu1 minus mu2. And so using this formulation, you can see the formula here, we get a 95% confidence interval that ranges from negative 43.07 up to 155.57. And notice that because that interval contains 0, 0 is a plausible value for mu1 minus mu2. And so we know, based on this interval, even if we had not done the hypothesis test on the previous two slides, even if this is all we had, this confidence interval for mu1 minus mu2, we would know that we could not reject the null hypothesis that the two population means are equal, all right, because the 95% confidence interval includes 0. All right, next we're going to compare mu1 and mu3. And so in this case, the null hypothesis is that mu1 is equal to mu3 against the alternative that mu1 is not equal to mu3. Stated in terms of a difference, the null hypothesis would be that mu1 minus mu3 is equal to 0 against the alternative that mu1 minus mu3 is not equal to 0. All right, the linear combination of that particular contrast is given here. So mu1 plus 0 times mu2 plus a negative 1 times mu3 plus 0 times mu4. And so we can pull off the contrast coefficients here. So A1 is equal to 1, A2 is equal to 0, A3 is equal to negative 1, and A4 is equal to 0. All right, and so we use those coefficients in order to construct the test statistic and so forth. So T-calc is going to be that same linear combination, but of the sample means, and that turns out to be y bar 1 dot minus y bar 3 dot. And then we would use those coefficients to get the denominator of the test statistic as well. Now, the critical point is again 2.1788, and so the rejection criteria is to reject the null hypothesis if the absolute value of T-calc exceeds the 2.1788. All right, so the point estimate of mu1 minus mu3, which is given by y bar 1 dot minus y bar 3 dot, that point estimate value was 46.0. All right, the estimated standard error of that point estimate is 45.5868. And so the calculated value of the test statistic is 1.0091. And again, since that is not greater than 2.1788, we would fail to reject the null hypothesis. And so at the 0.05 level of significance, there is insufficient evidence to conclude that mu1 and mu3 are different. A 95% confidence interval for mu1 minus mu3 ranges from negative 53.32 up to 145.32. And again, because that confidence interval, that 95% confidence interval, includes 0, we know that the null hypothesis, or we would not be able to reject the null hypothesis that mu1 and mu3 are equal. We would not be able to reject that at the 5% level based on this confidence interval. So again, we get, we can answer the same type of question using a confidence interval that we can with a hypothesis test. But with a confidence interval, we get more information. We get, not only are we able to make a qualitative decision about whether to reject the null hypothesis, but we get a set of plausible values, or the values that we think that are reasonable or plausible that the difference mu1 minus mu3 could potentially take on. Okay, and then the comparison of mu1 and mu4. All right, so the null hypothesis is that mu1 is equal to mu4. That translates into a difference, or stated in terms of a difference. mu1 minus mu4 equal to 0. The alternative would be that mu1 is not equal to mu4, stated as a difference. That would be mu1 minus mu4 is not equal to 0. The contrast coefficients we see are 1, 0, 0, and -1 for A1, A2, A3, and A4 respectively. And so we use those in calculating the test statistic. All right, and so the numerator of the test statistic is y bar 1 dot minus y bar 4 dot, and then we would use those same contrast coefficients in calculating the denominator, the estimated standard error of that difference in the numerator. The critical point, again, is 2.1788. It's going to be the same value for all of these pairwise comparisons. The point estimate of mu1 minus mu4 is negative 132. All right, the estimated standard error of y bar 1 dot minus y bar 4 dot is 45.5868 using this calculation. You notice here that this is the same value for each of these pairwise comparisons, and the reason is because there's equal replication. We had 4 observations from each of the 4 populations. Now, in this case, the value of the test statistic is negative 2.8956, the absolute value of which is positive 2.8956. And because that is greater than 2.1788, in this case, we do reject the null hypothesis. And so at the 0.05 level of significance, there is sufficient evidence. Let me see if I can highlight that there. There is sufficient evidence to conclude that mu1 and mu4 differ. And because y bar 1 dot is less than y bar 4 dot, we would therefore conclude that not only are they different, but we would conclude that mu1 is less than mu4. A 95% confidence interval estimate for mu1 minus mu4 ranges from negative 231.32 up to negative 32.68. So the 95% confidence interval estimate for mu1 minus mu4 ranges from negative 231.32 up to negative 32.68. Now, because 0 is not in that interval, and in particular because every point in this interval is less than 0, we are 95% confident that mu1 minus mu4 is less than 0. In particular, we are 95% confident that the difference between mu1 and mu4 is somewhere between negative 231.32 and negative 32.68. Another way to say that is we are 95% confident that mu4 is anywhere from 32.68 up to 231.32 units greater than mu1. Next, we're going to compare mu2 and mu3. All right, so the null hypothesis would be that mu2 is equal to mu3. against the alternative hypothesis, which would be mu2 not equal to mu3. Stated in terms of a difference, the null hypothesis would be mu2 minus mu3 is equal to 0. The alternative would be that mu2 minus mu3 is not equal to 0. The contrast that we're testing here, testing equal to 0 or comparing to 0, is 0 times mu1 plus 1 times mu2 plus negative 1 times mu3 plus 0 times mu4. And so the coefficients that define this particular contrast are a1 equal to 0, a2 equal to 1, a3 equal to negative 1, and a4 equal to 0. All right, the test statistic has numerator y bar 2 dot minus y bar 3 dot, and the critical point is again 2.1788. Now the point estimate for mu2 minus mu3 is equal to negative 10.25, as you can see here. That's the difference between the means of samples 2 and 3. Again, the estimated standard error of y bar 2 dot minus y bar 3 dot is 45.5868, and the calculated value of the test statistic is negative 0.2248. Now, since the test statistic has absolute value that is not greater than 2.1788, we fail to reject the null hypothesis. And so at the 0.05 level of significance, there is insufficient evidence to conclude that mu2 and mu3 differ. Now, a 95% confidence interval estimate for mu2 minus mu3 ranges from negative 109.57 up to positive 89.07. So again, 0 is in this interval, and so we see that we would not be rejecting the null hypothesis that means 2 and 3 are the same. All right, next, the comparison of mu2 and mu4. All right, and so the you see here the null and alternative hypotheses expressed both ways. The contrast coefficients for this particular comparison would be a1 equal to 0, a2 equal to 1, a3 equal to 0, and a4 equal to negative 1. All right, and so the numerator of the test statistic will be y bar 2 dot minus y bar 4 dot. The formula for the estimated standard error would be calculated using the coefficients identified on the previous slide, but the calculated value is going to turn out to be what it has been in the past, because again we have equal replication. The critical point is again 2.1788. All right, and so now we calculate the point estimate of mu2 minus mu4. This is the numerator for the test statistic, and that is obtained by calculating the difference between y bar 2 dot and y bar 4 dot, and we get a value of negative 188.25. All right, the estimated standard error of y bar 2 dot minus y bar 4 dot is again 45.5868. And so the calculated value of the test statistic is negative 4.1295. The absolute value of that, positive 4.1295, is greater than 2.1788, and so we reject the null hypothesis. At the 0.05 level of significance, there is sufficient evidence to conclude that mu2 and mu4 differ, and since y bar 2 dot minus y bar 4 dot, since y bar 2 dot is less than y bar 4 dot, we would therefore conclude that mu2 is less than mu4. A 95% confidence interval estimate for mu2 minus mu4 ranges from negative 287.57 up to negative 88.93. Since every point in this interval is less than 0, we are 95% confident that the difference between means 2 and 4, so mu2 minus mu4, is less than 0. And in particular, we could say that we are 95% confident that the difference mu2 minus mu4 is somewhere between negative 287.57 and negative 88.93. We can also express that by saying that we are 95% confident that mu4 is anywhere from 88.93 units up to 287.57 units larger than mu2. All right, and then finally the last comparison, comparison number 6. We are comparing mu3 and mu4. The null hypothesis is that mu3 is equal to mu4 against the alternative that mu3 is not equal to mu4. Expressed in terms of a difference, the null hypothesis would be that mu3 minus mu4 is equal to 0 against the alternative that mu3 minus mu4 is not equal to 0. The contrast coefficients would be a1 equal to 0, a2 equal to 0, a3 equal to 1, and a4 equal to negative 1. All right? And so the numerator of the test statistic would be y bar 3 dot minus y bar 4 dot. All right, we would calculate the estimated standard error of that point estimate according to this formula in the denominator. And the criteria is to reject the null hypothesis if the absolute value of t-calc exceeds 2.1788. The point estimate of mu3 minus mu4 turns out to be negative 178. All right, the estimated standard error of y bar 3 dot minus y bar, the estimated standard error, yes, of y bar 3 dot minus y bar 4 dot is 45.5868. And so then putting these together, the calculated value of the test statistic is negative 3.9046, the absolute value of which is greater than our critical point of 2.1788, and so we reject the null hypothesis. And so at the 0.05 level of significance, we conclude that there is sufficient evidence to conclude that mu3 and mu4 differ. Since y bar 3 dot is less than y bar 4 dot, we conclude that mu3 is less than mu4. The 95% confidence interval estimate for mu3 minus mu4 ranges from negative 277.32 up to negative 78.68. 0 is not in that interval, and in particular, every point in this interval is less than 0. And so we are 95% confident that mu3 minus mu4 is actually less than 0. And in particular, we're 95% confident that the difference mu3 minus mu4 is anywhere from negative 277.32 up to negative 78.68. And again, another way to say this would be that we are 95% confident that mu4 is anywhere from 78.68 units up to 277.32 units larger than mu3. Okay, so those are the 6 comparisons, and it takes a lot of work, doesn't it, to do these things by hand. Now, the good thing is that we can have SAS do this work for us, all right? And so in order to perform these specific comparisons, to perform not only the hypothesis test, but to get point estimates for the differences between the means, we're going to use contrast statements, and we're going to use estimate statements. Now, we haven't talked about the estimate statements, but we will in this context. Again, the contrast statements, which we've looked at, allow us to perform these comparisons to test these hypotheses. The estimate statements will also test those very same hypotheses, and you see here that the syntax is exactly the same, or the way we specify what we're testing is exactly the same as we do with the contrast statements. But the additional thing that the estimate statement will provide is a point estimate for the difference, or the point estimate for the contrast that we're actually testing hypotheses about. All right, and so these contrast and estimate statements will do all of those calculations with the exception of calculating the confidence intervals. We'll see how to do that in a second. All right, so let's look at these results. And so we have the 6 comparisons that we have performed by hand. And notice that when SAS reports the results from the contrast statements that it's giving us an F value, an F statistic. Now, when we did those comparisons, we calculated a T statistic instead. But remember, if we square the value of that T statistic, we'll get the F statistic. So if you take those T values that we calculated by hand and square them, then you will get the exact same values for these F statistics. Now, the additional thing that we'll get from the SAS output are p-values, and those are given here in the last column. And you can see here very easily, if we were performing all of these tests at the 0.05 level of significance, which is what we were doing, then which of these p-values are less than or equal to 0.05? Well, the comparison of mean 1 with mean 4, with mean 2 and mean 4, and mean 3 and mean 4. So this p-value is 0.0134, this p-value is 0.0014, and this p-value is 0.0021. So those are the only comparisons that are significant at the 0.05 level of significance. So we can tell by looking at these results that the differences that exist. Remember, we tested the overall null hypothesis that all four population means were equal. We rejected that null hypothesis. All that did was tell us that at least one of the means is different than the others. It did not tell us which means differ from which. Well, based on these follow-up pairwise comparisons, what we can see that mu4 is, we've concluded then that mu4 is different than mu1, mu2, and mu3. We have not been able to show that mu1 and mu2 differ, that mu1 and mu3 differ, nor that mu2 and mu3 differ. So that is where the differences lie. Here are the results from the, let me see here, from the estimate statement, all right? And notice that instead of F values, the estimate statement gives us T values. So if you go back and compare these values with the values that we calculated by hand, you'll see that we get the exact same thing. Now, we also get p-values, and you'll notice that these p-values on this page, let me go back one slide, are the same as the p-values on the previous page. All right, and so we're testing the same thing. We're just using the contrast statement on the previous page and the estimate statement on this page. Now, notice that the estimate statement gives us point estimates for the contrast that we're testing hypotheses about. So the point estimate for mu1 minus mu2 is 56.25. The point estimate for mu1 minus mu3 is 46.0, and so forth. And if you go back, you'll see that those are the exact same values that we got when we calculated them by hand. Note also that the estimate statement gives us the estimated standard errors associated with each of these point estimates, and that the estimated standard error in each case is 45.5868 if we round it to 4 decimal places, which is exactly the same value that we got when we calculated it by hand. All right, and so you see the differences between what the contrast statement and the estimate statement provide, but you also see the commonalities. They both test the same hypotheses. Now, the estimate statement in Proc GLM does not provide the confidence intervals, though. Does not provide the confidence intervals for the contrast that we were testing hypotheses about. To get those, we would have to use a different procedure. The way that we use the procedure is going to be the same way, but it's a newer procedure. It has additional capabilities, and that procedure is Proc mixed. Now, we can use Proc mixed even though this is not a mixed model situation, right? We don't have a random effect. We don't have any blocking or anything like that. All right, but we can still use Proc mixed. So we invoke Proc mixed. We still have to specify to Proc mixed the classification variable, which is variety. We specify the model in the same way. The yield is the response variable. Variety is the variable that identifies the different groups or populations. And then I'm not going to repeat the contrast statements. We've already done that in GLM. You're not going to get any different output from proc mixed from the contrast statement. But the estimate statement in proc mixed has an option that we can use to get the confidence limits. And that option is CL. And so after the contrast coefficients, we put a forward slash, and then the CL option, and that tells SAS proc mixed to produce not only the point estimate for the contrast that we've specified, but also to construct a confidence interval. And so we see here on this part of the SAS output, we see that we get the lower and upper confidence limits. And these are confidence limits for a 95% confidence interval by default. And so if you go back and compare these lower and upper confidence limits to the ones that we calculated by hand, if you compare those, you'll see that we get the same exact limits. But the great thing is that it's much quicker using proc mixed. So all of these calculations, all of these custom hypotheses, these specific comparisons, are very, very easily performed in SAS, either in proc GLM or in proc mixed. And the only thing we have to do is to specify the custom hypotheses that we want to test. And we do that using either the contrast statement or the estimate statement. So the contrast and the estimate statements in proc GLM and proc mixed allow us to perform pairwise comparisons as well as to test other more general custom hypotheses. But if pairwise comparisons are all that are required, then there's an even easier way to do this in SAS. The following code shows how to use the ls mean statement in proc GLM to perform all pairwise comparisons, and you can do the same exact thing in proc mixed. All right, and so instead of specifying the custom all those the 6 different contrasts or the 6 different estimate statements, all we have to do, if all we want are the pairwise comparisons, then we just use this line right here. All right, so ls means variety being the classification variable that identifies the different groups or populations. All right, and then we issue, after the forward slash, we issue the pdiff option, and that what that tells the ls mean statement to do is to produce the p-values for the pairwise comparisons. And then SAS will automatically produce some graphics, but I'm showing how to ask for those graphics specifically, and in the case of the first plot, which is called the mean plot, how to request the confidence limits for the confidence intervals for the individual population means. All right, so let's look and see what the output looks like. And so here is the tabular output. We see the estimated values for the population means for the 4 varieties. And then in the subsequent table, these are the p-values for comparing the pairwise comparisons of the population means. And so, for comparing mu1 and mu2, and so the rows and the columns correspond to a population number. So if we want to compare population means 1 and 2, this is the p-value for that comparison. Now, if you go back and compare that to the p-value that we got using the contrast statement, you'll see that that's the exact same p-value. The p-value comparing mu1 and mu3 is 0.3329. And then the p-value comparing mu1 and mu4 is 0.0134. The p-value for comparing mu2 and mu3 is 0.8259. The p-value for comparing mu2 and mu4 is 0.0014. And then finally, the p-value for comparing mu3 and mu4 is 0.0021. And so we could look very quickly at this table of p-values and see that we could identify where the differences are. We see that mu4 is different than mu1, mu2, and mu3, but that there are no differences between mu1 and mu2, mu1 and mu3, and mu2 and mu3. Okay, so here is a plot of, let me go back one slide. These values here, these estimated population means, are represented by the circular points on this graph. And then the intervals here, these are 95% confidence limits for the corresponding variety means. So that's what is indicated up here in the titling of this plot. All right, and the reason it's giving us those confidence limits because we requested it in parentheses after the mean plot statement. If all we had was mean plot without that part right there, then it would not give us the intervals, it would only give us the locations of those circles. Now notice here that the confidence intervals for mu1, the confidence intervals for mu1 and mu4 overlap. There's some overlap there. If we were, some people like to use the confidence intervals for the individual means to make a determination as to whether the population means are different, right? And the thinking is that if the clearly if the confidence intervals don't overlap, then that would indicate that we would conclude that the population means are different. But they would also say that if the confidence intervals do overlap, then we cannot reject the null hypothesis that the population means are the same. We cannot conclude that the population means differ. However, we did, in comparing mu1 and mu4, we did reject that null hypothesis of equality, right? In fact, there was fairly strong evidence that the population means mu1 and mu4 are different. And so you can see here that this is a very good example that even though these confidence intervals for mu1 and mu4 do overlap, all right, that's really not the most powerful way to compare those two population means. The more powerful way, the better way, is to make an inference about mu1 minus mu4, and that's what is being done in this test. And it's also what's being done in the next graph that we'll look at. This is called the, let me see here, it's called the diff plot, the mean diff plot. And this is a really interesting and very useful plot. The way you read this is that you see here we've got a series of, we have 4 vertical lines and we have 4 horizontal lines. Now the vertical line is positioned at a point that corresponds to the estimated mean for that particular line. So mu2 has a value that is, let's see here, what was it? It was 928.25. So that is the location of that vertical line. That is also the location of this horizontal line. So the vertical and horizontal lines correspond to a particular estimated population mean value, all right? And so the location of the vertical line and the horizontal line, again, corresponds to that estimated value. Now, let's suppose that we want to compare mu2 with mu3, mu1, and mu4. All right, and so what we're going to do here is look up, we find this vertical line corresponding to the second population, and we see here that where it intersects with mu3, or the line for population 3, we see this diagonal line. Now, the midpoint, or the interval itself, the length of this diagonal line corresponds to a 95% confidence interval estimate for mu2 minus mu3. And the way we interpret this is that if the diagonal line intersects the equiangular line, then that would the conclusion that we would draw is that the two respective means are not different. And so this diagonal line intersects the equiangular line, and so we conclude that mu2 and mu3 are not significantly different. All right. We see here that this this diagonal line also intersects the equiangular line, so we conclude that mu2 and mu1 are not different. All right, and then finally, this diagonal line, it also intersects the equiangular line, and so we would conclude that, let's see here. Oh no, that's a different comparison. So what next we would do is go up here, and we would look at this blue line. All right, so that has a midpoint at corresponding to the vertical line, where this is population 2 and then population 4. And so since that line does not intersect the equiangular line, then we would conclude that mu2 and mu4 are significantly different from each other. Basically, when you see these blue lines, all right, that's telling you, that's an easy way to see, because sometimes with a lot of comparisons, this gets really busy, and so by color coding it, they help us to see which population means are different from each other. And so this would tell us that means 4 and 2, 4 and 3, and 4 and 1 are different. So mu4 is different than mu2, mu3, and mu4. These red dashed lines, because you can see they all intersect the equiangular line, we conclude that these are non-significant differences, and so we would conclude then that mu1 and mu3 are not different, mu1 and mu2 are not different, and then mu2 and mu3 are not different. So this is a really nice graphical array to show the results of all those different comparisons that are being performed. But again, if you do have lots of comparisons, pairwise comparisons that are being done, this can get somewhat busy. But for this small number of comparisons, the 6 comparisons, this very, very nicely summarizes the overall results of these comparisons. And so, again, we perform the analysis of variance to compare the mean yields for the 4 rice varieties. We rejected that null hypothesis of equality and concluded that there were differences among the means. The natural question then, as a follow-up, is where are the differences, which means differ from each other. And so this tells us that mu4 is different than mu1, mu2, and mu3, but mu1, mu2, and mu3 are not different from each other. All right, so that is how to perform custom hypotheses in SAS using the contrast statement, using the estimate statement. We also saw how to do this by hand. All right, and so that is what I wanted to review for your from your first methods class. And so we will continue on with new material in the next set of lectures.